Ever try picturing a shape with more dimensions than you can even imagine?
Yeah, it'd make your head spin, wouldn't it?
Well, that's what we're diving into today. Hypercubes, it's like someone took a square and said, hold my drink.
And to help us navigate this multidimensional maze, we've got a math whiz right here with us.
So what exactly I ask a hypercube?
You're right. It's not like something you can just draw on a whiteboard.
Yeah, good luck sketching that one out.
But here's the thing. Even though we can't really picture a hypercube in our minds, we can still use math to explore its properties. Think of it this way. You might not understand how a car engine works, but you can still appreciate how it makes the car go.
I like that. So less about actually seeing the hypercube and more about understanding how it ticks, right?
Exactly.
Yeah.
Like take a square. It has 4 points, 4 lines connecting them. Cube, 8 points, 12 lines. A hypercube just keeps adding dimensions. More points, more lines, more connections.
And that's where things get really interesting. That's where we start talking about polynomials.
Yes. Polynomials.
All right, gotta admit, that one sounds a little intimidating. You're gonna have to break that one down for me.
No worries, it's not as scary as it sounds. Just think of a polynomial like a mathematical sentence.
A sentence.
Yeah. It describes relationships.
Okay.
And these sentences can be simple or super complex, but they're always telling us something important about how things work.
So in our case, how things work in the world of a hypercube, which, by the way, today's deep dive is all about.
Yeah.
It comes from a brand new research paper looking at how these polynomial sentences act on a hypercube.
And let me tell you, they get up to all sorts of mischief.
Oh, really? Like what?
Well, the big mystery is what happens when these polynomials vanish.
Vanish. They just disappear.
Well, not exactly disappear. Imagine a light switch that's not connected to a bulb. You know, it's there, but it's not doing anything. When a polynomial vanishes at a point on a hypercube, it means it equals 0 at that specific location.
And that 0, that's not just a random number, right? That's a clue.
You got it.
A clue to what? What's so important about whether or not a polynomial takes a little nap at certain points on a hypercube?
Because it actually affects a bunch of different fields. We're talking things like computer science, cryptography.
Wow, really?
Yeah. This is serious stuff. We're talking the building blocks of secure communication, online security, the whole 9 yards.
Okay, so understanding these polynomial properties has a ripple effect.
A huge one.
Okay, so we've got these hypercubes, multidimensional, kind of spooky, and these polynomial sentences leaving their mark all over the place. Sounds like we've got ourselves a real mathematical mystery on our hands.
You could say that. And like any good mystery, this one's got a whole history to it. Brilliant minds, piecing things together, you know.
So who were the first detectives on the scene trying to crack this hypercube case?
Well, we got to rewind all the way back to 93. Alon and Füredi, these two mathematicians, they made a huge discovery about these vanishing polynomials.
Oh, yeah.
They figured out that if a polynomial vanishes everywhere on a hypercube except for the very center.
Kind of like a single spotlight in a pitch black room.
Exactly. They found that to pull that off, the polynomial itself had to be incredibly complex.
Complex how?
How can I explain this? Imagine you're trying to make a single beam of light appear in a room full of mirrors. You'd need a crazy setup, right? Angles, reflections, the works. Well, Alon and Füredi proved that to have a polynomial vanish everywhere but the center, you need a crazy complex polynomial to do that.
Oh, okay, I think I'm starting to get it. So where the polynomial vanishes tells us something about how intricate the math behind it is.
Like a fingerprint at a crime scene.
It's a clue, right?
A big one. But the story doesn't end there.
Of course not. There's always a plot twist.
Fast forward to 2023, two other mathematicians, Sziklai and Weiner, they come along and realize this vanishing act, it's not just limited to the center.
Really?
Yeah. There are other points on the hypercube where this works too. You just got to know where to look.
So they found like a hidden pattern, other places on the hypercube where these polynomials go silent.
Exactly. And they use some serious mathematical firepower to figure it out. I'm talking Möbius inversion formula, Zeilberger's algorithm.
Sounds complicated.
Oh, it is, but trust me, it's elegant stuff.
So instead of magnifying glasses, they used crazy math equations.
Pretty much.
Yeah.
They found a way to look at where the polynomial wasn't vanishing and use that to predict where it would vanish.
Like a reverse code. Okay, so they're mapping out the safe zones on our hypercube, the places where our polynomials can hang out without disappearing.
You got it. But wait, there's more.
There's always more.
2024. This mathematician, Hegigis, he takes Sziklai and Weiner's work and says, hold on, I think we can make this even more precise.
Oh, he's upping the ante.
Big time. He comes up with a new theorem, right? Even more powerful. It's like giving our hypercube detective a high-powered magnifying glass. Lets us see these relationships in even clearer detail.
Okay, so we went from blurry Polaroids to 4K resolution.
Exactly. Hegedus showed us just how deep this rabbit hole goes, how interconnected these ideas really are.
And this leads us to...
The research we're going to delve into today.
So we followed the clues through decades of research, and now...
We're at the doorstep of a brand new discovery.
a fresh case file.
Exactly. This paper we're diving into today, about almost covering subsets of the hypercube. It's like the climax of our mathematical mystery.
Okay, I gotta ask, almost covering subsets, so we're not even looking at the whole hypercube anymore.
You're catching on. Think of it like you're trying to map out a huge maze, right? But you can only peek through certain holes in the walls. Those are our almost covering subsets, giving us glimpses into the hypercube.
And what are we trying to see through these little holes?
We want to know, can we figure out how complex a polynomial is just by looking at where it vanishes?
So if we know where the polynomial doesn't exist, we can know how complicated it is.
Exactly. And the way they figured this out, pure genius, they used this thing called the Möbius inversion formula.
Wait a minute, isn't that what Sziklai and Weiner used?
You got it.
It's all coming together. This new research is taking everything that came before and pushing it even further.
Like they took Hegedus's blueprint, zoomed way in, and found a secret room nobody knew about.
Okay, I'm sold. This is way more exciting than I thought hypercubes could be. But all this math, how does it actually affect us in, the real world?
Think about online security. Every time you log onto your bank account, send an email.
Pretty much everything these days.
Right. All that relies on complex algorithms. And guess what? Those algorithms, they're built on the exact same math we're talking about.
No way. So hypercubes are basically holding the internet together.
In a way, yeah.
Huh. Who knew these abstract shapes held the keys to the digital kingdom? Makes you wonder what other mathematical mysteries are still out there.
Just waiting for someone to shine a light on them.
And that's what we're all about here on the deep dive. Taking the complex and making it, well, if not simple, then at least totally fascinating. Thanks for joining us, everyone, and until next time, keep those minds curious.